We'll be looking at the question 22 from the October 2021 paper. The first question is, this whole question is about acid, bases, and buffers. Wait a minute, let me just check if, is my sound recorded? Yep, oops. Just wanted to check that my voice is being recorded. The first question is about a strong base, and dealing with sodium hydroxide. You've got the concentration of sodium hydroxide, and it wants us to calculate the pH. So this is a straightforward question. We're going to use the expression Kw is equal to the H plus concentration multiplied by the hydroxide concentration. At standard temperature, we know that this is also equal to 1.0 times 10 to the minus 14. By the way, today's episode is being recorded by in front of a live audience. Moles squared and dm minus 6. Now you see, because this is a strong base, we assume this concentration of 0.140 is also the same as the concentration of the hydroxide ion. So all we do, we substitute that value in. So H plus concentration is multiplied by 0.14 is equal to 1.0 times 10 to the minus 14. Rearrange that and plug that value into the minus log to the base 10 of the H plus. And you see, in this question, you could spend all the hard work in doing the question and not read it carefully. They want it to 2 decimal places. So let's do this. Two decimal places, that gives 13.15. Very good. Next question. Next question, sulfuric acid reacts with sodium hydroxide as shown below. This is a neutralization reaction. This is a neutralization reaction. And, okay, they want us in this question, in the second part of part B, they want us to work out the enthalpy change of neutralization. This is a good time to remind you of the definition of enthalpy change of neutralization. You see, if you look at the glossary of terms, either in your textbook or in the spreads, the standard enthalpy change of neutralization, I've got the wording here. I'll read out the wording here and I'll give you the concise, what the examiners are looking for. There's the enthalpy change that accompanies the reaction of an acid and a base. And as you know, all definitions always refer to 1 mole. Acid and a base go on to form 1 mole of water in this case. This is the enthalpy change of neutralization. As you'll notice in the overall equation, delta H1, this is how many moles of water are forming? 2. And so we need to be mindful of that when we do part 2. It's asking, show that NaOH is in excess. So with NaOH, you've got, let's work out the moles. Let's convert to decimeters cubed and multiply by the concentration. This is for NaOH. And for sulfuric acid, it tells you that the NaOH is in excess. But let's have a look at why is it in excess. You've got H2SO4. Again, volume times concentration. 0.0400. You see, ladies and gentlemen, there's two ways of doing this. As we spoke earlier, the enthalpy change of a reaction is dependent on the limiting reagent, whatever's limiting. Now, you see sulfuric acid and NaOH are reacting in a 1:2 ratio. So if we look at NaOH, which is 0.0825 moles, this will react with 0.04125 moles. And you can see that it reacts with more than the sulfuric acid that is present. That's why it is in excess. Let's have a look at the mark scheme. 1 mark for these two. You get a mark for that. And 1 mark one mole. Yep, you'd either get 1 mark for that or 1 mark for that. We good? Moving on. Right, this is the more sort of a significant question. It's asking, what other values have they? Oh, they've given you a temperature change in here. We need to use that. The temperature increases by 13 degrees Celsius. A student asked a question where they said, do we need to convert the degrees Celsius into Kelvin for when we use Q equals MC delta T? No, we don't. Because this is temperature difference, it makes no sense. There's no reason. If we're going from 298, say 293 to 298 Kelvin, or 22 degrees Celsius to 25 degrees Celsius, it's still a 3 degree or 3 Kelvin difference. So it doesn't make a difference. It's still 3 degrees Celsius or Kelvin. So it doesn't make a difference. We'll stick to degrees Celsius. Okay, so if you've been following Chana daily, you'll notice this expression Q equals MC delta T has come up a few times. Now, in here, M is the mass of the medium of the two solutions combined together. 25 plus 55, which gives us 80. 80, because we assume 1 centimeter cubed is equal to 1 gram. C is 4.18, and if you look at the units are very revealing. It's joules of energy required to heat 1 gram of water by 1 degrees Celsius. And then you also multiply this by the temperature difference, which was given as 13. That gives you 434.2 joules. You see, we're trying to convert joules to kilojoules per mole. So there's two things we need to do. We need to divide that by 1,000 and divide it by the number of moles of the limiting reagent. We've already worked out the moles of the limiting reagent, which is H2SO4. So we've got 4347.2 divided by 1,000 and divided by 0.04. That will give you your answer. And a very important thing here, we need to, because the temperature is increasing, it's exothermic. Do you agree? Yep. And if it's exothermic, it's going to have a minus sign in front of it. If you don't put that minus sign, you will lose marks. So let's work this out. How many sig figs does it want? It doesn't really say. We'll do, if it doesn't say how many sig figs, 3 is the good standard. So we'll use that as, we'll write the whole value down, but 3 is generally good. Minus 108.68 kilojoules per mole. Ladies and gentlemen, this is for 2 moles of water forming, but for 1 mole of water forming, we just very simply divide that by 2. Okay, let's just look at the mark scheme if that supports it. In the mark scheme, there's a separate mark. If you got everything wrong, but you got the sign right, you get 1 mark. Yeah, such a very easy mark to get. So please be mindful of that. Yep, minus 54.34 is your answer. Next question. The student repeats the experiment using double the volume of H2SO4 and double the volume of NaOH. Okay, now you see, if we go back to the expression, Q equals M times C times delta T. You see what we're doing, we are multiplying the mass by 2. And if we multiply the mass by 2, in the mass is the volume, in that volume is the moles. And because you're doubling it, it's going to double the amount of energy that's given off. That's also multiplied by 2. There's a direct correlation. And because the mass, the concentrations are kept the same, but the volumes are doubled, the energy doubles. But the temperature change is still going to be the same. This will still be constant. In this case, 13 degrees Celsius, as it was mentioned in the question. So this is worth 2 marks. Putting that into words, double the energy is spread in double the volume or mass. Okay, and just saying that the temperature will be constant or the same. Same is probably a better word. They've used same, I said constant. Or 13 degrees gives you a mark. Yes, Huda? So why do you have to keep it constant? Sorry. Okay, no, but maybe let's take away the word constant. You see, because the mass is changing, the temperature difference is going to be the same. Why is it? Because you've got the energy is doubled, but that doubled energy has spread through double the volume. So it doesn't affect the temperature. Temperature change is going to be the same. Okay. By the way, this type of question comes up quite often. These type of questions. This is going to be the difference maker. This will help you access the high grades. Okay. Moving on. Now here, I believe this is the last question. Yes, it is. Right, how many marks is this worth? 6 marks. Now, this question, a 6-marker question with all this information, and you see all those lines, there's a psychology behind that. Would you agree? Yep, it can be daunting. Do not worry. You take a deep breath and you get your highlighter out or your you know, as some students like to do, underline or circle, and you read through it and you extract the relevant, useful bit of information. Nitrous acid is a weak acid, and it's got a pKa value of 3.34. HNO2 can be prepared by reacting that with water. I don't know if we're going to need that. Oh, maybe we will need that. So you got N2O3 reacting with water. HNO2 is the only product. The chemist makes up a buffer solution by the following method. So the chemist weighs a sample of N2O3. Water is then added to form this volume and this concentration of nitric acid. So we got what we got here is a volume and a concentration. The chemist adds this much, let's use a different color pen for this volume and this concentration of sodium hydroxide to that original solution. And then the resulting solution is made up to 1 decimeter cubed. Explain why a buffer solution forms in step 2, determine the pH of the buffer solution, and so why buffer solution forms, and determine the pH of the buffer solution and the mass of N2O3 that was used. A lot of information there. Let's now break it down. You see, when we're using a buffer solution, there's a few things here. Let's look at we're going to flip-flop. So we may look at the beginning and the end, and then the middle in no particular order. You see, just looking over here, you've got N2O3. If that's reacting with water, that gives you HNO2. And it is a 2-to-1 ratio. So that ratio will come in use a bit later on. You're looking at a buffer solution. Look, I'm looking at the very first step there. And the buffer solution, if you've got a weak acid and its conjugate base, you've got this setup here. Now, we're going to use the Ka expression, which is going to be these products over the reactant, which is dissociating NO2 minus H plus over and just a reminder, in this setup, I'm going to explain to you why a buffer solution has formed. But you see this NO2, this is not, we don't think of this as that's come from here. We've actually got a large reservoir of the NO2. That's why this is a conjugate base or your salt. And this is also what's going to be in your expression. And for this reason, when we're dealing with the K expression, it does not equal H plus squared. You know, we use this for weak acids. No, no, no. So we've got this. This is going to be our base foundation. Now let's do the calculations. You see, we've got for NHNO2, we've got in the question originally 100 centimeters cubed volume. We got the concentration. Now, this is reacting with sodium hydroxide. You got the volume concentration. You know, questions like this. If you get stuck and they give you volume concentration of something. An easy mark is just multiply them together. Yep, after dividing it by 1,000. You know that's going to come in use somewhere. Sodium hydroxide is over here. What am I doing? As you can see, when you react these two together, sodium hydroxide gets all used up. And so what you're going to end up with is HNO2. You will have 0.0350 moles. And for the sodium nitrate 3, which is this, you're going to have 0.0150. Where's that value come from? It's come from the sodium hydroxide that's formed the salt. Is that good so far? So we've got these values, and now these moles, they are made up to 1 decimeter cubed. So we're adding water to it and making up to 1 decimeter cubed. And because we're making it up to 1 decimeter cubed, these mole values are actually concentrations. Okay? And what we'll then do, so going back to the question, why a buffer solution forms, let's answer that question first. As a weak acid, as an excess of weak acid, HNO2 is reacting with a base, in this case, NaOH. Let me just check how they've worded that in the mark scheme. Yeah, acid is in excess. You get, that's a point there. Good. Now, going back to our Ka expression, Ka equals NO2 minus H plus over the weak acid, which is HNO2. And you see, we plug in pKa is given in the question of 3.34. So 10 to the power of minus 3.34 is over here. The salt or conjugate base, we plug that there. The weak acid, we've calculated, is going to be there. That leaves us with the H plus concentration. And we then just plug that in to our expression, minus log to the base 10 of that H plus concentration will give our answer. And we'll give it to, yeah, they don't ask for significant figures or anything. We'll just give it to 2 decimal places. So let me calculate that. 10 to the power. By the way, just a bit of theory here. You see 10 to the power of minus pKa is equal to Ka. That's why we're doing this. Once I've worked out Ka, let's multiply that by HNO2. We're bringing that up, multiplied by 0.0350, and then divide it by the salt conjugate base concentrations, divided by 0.0150. That gives you the H plus concentration. 1.06659 times 10 to the minus 3, and then minus log to the base 10 of the H plus concentration gives you 2.97. Yep. Let's have a look at the mark scheme. The mark scheme, yep, they want the pH 2 decimal places, so be mindful of that, which gives you, it makes it 3 significant figures. That's correct. Oh, we've not calculated the mass yet. Let's calculate the mass. You see, this is a, yeah, it is 2.97. And to calculate the mass, how do you do that? You see, how much mass was initially calculated? Ladies and gentlemen, the initial amount of HNO2 was 0.05 moles, the initial amount of the acid that was produced, HNO2. You see that HNO2 is a 2-to-1 ratio. How do you make 2 into 1? You divide that by 2. Let's just write this there. 0.0500. Let's divide that by 2. And this is for the N2O3 mass. That divided by 2, and then we're going to multiply that by the MR of N2O3, which will be 14 plus 14 plus 16 plus 16 plus 16. What does that give you? 28 plus 48, 76. Wonderful. So 0.05 divided by 2 multiplied by 76 gives you 1.9 grams of mass required. Ladies and gentlemen, that pretty much covers all that question. And I will see you tomorrow.